Hello students, in the last lecture I started discussing about photodiode, and there I discussed that a photodiode works in two modes, that is photoconductive mode and photovoltaic mode. So there are two modes of conduction of photodiode. So in this lecture I'll be discussing only the photoconductive mode of photodiode, because I've already discussed the photovoltaic cell in my previous lectures. So for photoconductive mode, that is when this photodiode operates in reversed biased mode, it is called photoconductive mode. Reversed biased means, as I've told you, this photodiode is made up of p-type and n-type layer. So reversed biased means when n-type is connected to the positive terminal of the battery and p-type is connected to the negative terminal of the battery, that is when negative voltage is applied at the anode and positive voltage is applied at the cathode, we say that the photodiode is connected in reversed biased mode. So this is when the photodiode will work in the photoconductive mode. Now let me discuss the working of photodiode mode. What happens? So as we know, I've already discussed the p-type semiconductor and n-type extrinsic semiconductor. I've already discussed in my previous lectures that what is p-type extrinsic semiconductor and what is n-type extrinsic semiconductor. So there I discussed that the electrons present in the p side, that is the electrons present in the p side and the holes present in the n side, are minority carriers. What I'm trying to say is, in p type what are the majority carriers? Holes are the majority carriers and electrons are the minority carriers, whereas in n type extrinsic semiconductor, electrons are majority carriers and holes are minority carriers. Now when the photodiode is reversed biased, when this photodiode, this is the actual internal diagram of the photodiode, this is p type, this is n type, and it is connected in reversed biased mode, that is p is connected to the negative terminal of the battery and n is connected to the positive terminal of the battery. So when the photodiode is reversed biased, then minority carriers, that is holes from n side, experience repulsive force from the potential, from this positive potential of the battery, that is this battery. From the positive potential of the battery, the holes will experience a repulsive force. That is, holes from the n side will experience repulsive force from the positive potential of the battery. Similarly, electrons present in the p side, that is the minority carriers of the p side electrons, will experience repulsion from the negative terminal of the battery. Now due to this movement, a very small reverse saturation current will flow through the device, and that is known as dark current. That is known as dark current. Why it is called dark current? Because this current is totally the result of flow of minority carriers and is thus flows when the device is not exposed to any type of radiation or light. That is, when there is no light illuminating, when there is no light illuminating in this on this photodiode, then the current that will flow through this photodiode is the dark current, and that current is the reverse saturation current, because the photodiode is operated in reversed biased mode. So the value of this reverse saturation current does not depend on the applied reverse voltage across the diode. Rather, it depends on the concentration of minority charge carriers in the semiconductor crystal. Hence, for a certain range of reverse voltage across the diode, this current almost remains constant. So we cannot, so we can control this reverse saturation current in a diode by controlling the concentration of minority charge carriers in the semiconductor crystal. And we can change this concentration of minority charge carriers in the semiconductor crystal by applying external energy to the crystal. Now in the photodiode we do the same, we apply this external energy. In the photodiode we actually do the same thing, that is we do the same to control the conductivity of device, because as the name suggests, in photodiode the PN junction gets exposed to light, and as light falls on the surface of the junction, then the temperature of the junction gets increased. This causes the electron hole pairs to get generated at the PN junction. At the depletion region, the electron hole pairs so generated gets separated, that is, the electron gets attracted towards the positive potential of the battery. Similarly, the hole gets attracted towards the negative potential of the battery. So this movement of electron holes so generated in the depletion region generates high reverse saturation current through the device. So this movement generates high reverse saturation current through the device. Now with the rise in light intensity, as we keep on increasing the light intensity, more charge carriers are generated and flow through the device, thereby producing a large electric current through the device. So we can say that the intensity of light is directly proportional to the current, or you can say the current through the device is directly proportional to the intensity of light falling on the depletion region of this photodiode. Now here one point you have to note here, it is that in a photodiode only the PN junction portion, means this depletion region portion, here also you can see in the constructional that the depletion region portion, only the PN junction portion of the diode must be exposed to light. This is because if light falls away from the junction, then electron hole pairs will get created from the junction. So what I was telling, if the light falls away from the junction, the electron hole pairs will get generated, but they will get sufficient time to recombine, hence they cannot contribute to the reverse current. But electron hole pairs generated or created in the junction or very nearby to the junction can propagate easily towards opposite polarity due to the influence of the electric field across the junction, due to this potential barrier of the junction, and hence the current through the photodiode gets increased. So it is important that the light should fall on the depletion region of the photodiode. Now this reduces the response time of the photodiode, because the additional reverse bias increases the width of the depletion layer, which decreases the junction's capacitance and increase the region with an electric field that will cause electrons to be quickly collected. So although this photoconductive mode is faster, that is the response time is less, but the photoconductive mode can exhibit more electronic noise due to dark current or avalanche effects. So the leakage current of a good pin diode is so low that the Johnson-Nyquist noise of the load resistance in a typical circuit often dominates. So this was about the working of the photodiode. In my next lecture, I'll be discussing about the characteristics, that is VI characteristics of photodiode, and advantages, disadvantages and applications. So I'm ending this class here. Thank you.